So welcome everybody. My name is Ben. We're going to be going and doing a two-part series on the GitLab Prometheus monitoring infrastructure. Part one is going to be an overview of all the architecture and the current state of our infrastructure. And then part two, we're going to do some failure scenarios and debugging. So let's get this started. So the core component of our monitoring infrastructure is the Prometheus server that does the collection, storage, and evaluation of metric data. And so if you're not familiar with Prometheus, there's lots of good videos on Prometheus itself, how it works, what it does. It's an active monitoring system. It collects data from all of our different components. It aggregates it into a time series database, and then it allows you to evaluate that data and send it upstream. So of course, our infrastructure is medium size. It takes more than one Prometheus server to do all the work. And what the design of Prometheus is that the Prometheus server should live close and operate close to the data that it's and the systems that it's monitoring. And so we have multiple GCP environments currently, and each of those GCP projects is a separated, isolated network. And so within that network, there are one or more Prometheus servers. So in staging, there are Prometheus servers. In gprod, there are Prometheus servers. In et cetera, et cetera. And so each of those Prometheus servers is doing its work, monitoring all the things. And in the Prometheus design, there's also high availability. And the way Prometheus does high availability is the individual monitored components are agentless metrics endpoints, and they're stateless in the fact that they don't, individual monitored endpoints don't maintain their history. That's Prometheus' job. So they only expose their current latest data. And so in order to have high availability, you have two Prometheus servers in locks, with identical configurations, duplicating the data. And then now we have duplicate data. Now we have and high availability pairs. In addition, we have multiple Kubernetes clusters in our environment. So within one GCP project like gprod, we have different multiple Kubernetes clusters, and we also have multiple services running under Chef management at this time. And within each of those environments, there are individual Prometheus servers. So there's a zonal cluster, zonal services, zonal Prometheus. And so yeah, so now we have somewhere around 50 individual Prometheus servers monitoring different things. They're all different sizes. They range anywhere from very small of tens of thousands of metrics to our biggest regional Kubernetes cluster has somewhere on the order of about 5 million metrics at peak traffic scaling time. So as the pods auto scale up, there are more metrics for each pod, and therefore the Prometheus server grows a bit during the day. And of course, when we do deploys, there's also some churn because we have duplicated metrics for each pod as we roll out. And so the Prometheus server can go up from a couple of million metrics to 5 or 6 million. And so you have to kind of make sure that the Prometheus server has enough resources. But now how do we actually access all this data? Well, on top of Prometheus, we use an overlay layer clustering software called Thanos. And so Thanos is a microservice-based aggregation system. And what it does is each Prometheus server has a Thanos sidecar that does a couple of different things. The sidecars are connected to object storage. So each Prometheus server has writes out data to its local disk, and the sidecar backs up that data every 2 hours, every 2 hours, Prometheus writes out a time series block, and then those blocks are uploaded by the sidecar into object storage and Google Cloud Storage in this case. And once that's up in object storage, those blocks can now be read and served by a Thanos storage server. And so the Thanos storage server is basically a front end in front of object storage for reading Prometheus data. But how do we actually run Prometheus queries against all these different sidecars and storage servers? Well, there's a Thanos microservice called the query server, and the Thanos query server uses a gRPC API to fan out Prometheus queries out to all of these storage servers and sidecars. So because it takes 2 hours minimum to upload that data from Prometheus to GCS, we still need access to the latest data that is only in the individual Prometheus servers. And so the query server queries from the query server, it makes a data request to the sidecar, and the sidecar fetches the data from Prometheus's memory using a remote read protocol. The Thanos query also has a bunch of other smarts. It knows how to deduplicate. So based on one of the Prometheus servers have a lot of labels. There are labels that come from the metrics, there are labels that come from the target discovery, and then there are external labels. And so Prometheus uses the external labels, or Thanos uses the external Prometheus labels to provide a routing tree in order to reduce the queries. So if you query for env equals gprod, Thanos is smart enough to only send the queries to the gprod storage and sidecars. This makes it so that you can, it's much more efficient to query against all these different endpoints. So say you wanted to get only one zonal cluster's Prometheus data, I believe there's an external label that you could filter for that. But most of the time we just fan it out to all, we're actually not really interested in individual zonal clusters, so we just fan it out to everything in gprod or everything in gstage. I have in a recent merge request, we've been working on the, let me see if I can pull this up. We've been working on a readiness review for the current state of the Thanos infrastructure. And there's a nice diagram in the doc. Here we go. And if I share this, we can kind of take a look at this. And so now we can see where we have the Prometheus servers and their sidecars. They upload to the GCS buckets. The Thanos stores read from the GCS buckets. The Thanos stores have memcache for accelerating queries. The Thanos query can access these stores in the sidecars. And that kind of, that covers what we've talked about so far. Is the diagram good?
It's definitely helpful. I was looking for this. I'm in the process of updating the handbook architecture pages, and I was having trouble finding this diagram. So maybe we should move this to runbooks eventually or something. I don't know, like to make it a little bit easier to find. Sure. I didn't think of looking in readiness, but this is probably the most up to date version that we have.
Yes, this is not yet merged, so this will be coming soon. And then we can copy it to other places. Unfortunately, this diagram it is also not even complete. There are lots of lines that I couldn't add because the mermaid diagram app just choked on the complexity. Unfortunately, for example, Thanos query also connects to Thanos rule, because Thanos rule is kind of a Prometheus server, and the Prometheus servers also connect to the alert manager, and that extra line just made the whole diagram blow up. It just wouldn't render. Don't know. Need better diagram software than Mermaid. Okay, so we've covered the storage, the sidecars, the query server. Let's talk about Thanos Compact. So every 2 hours, each Prometheus server is uploading to GCS via its sidecar. That generates a lot of blocks. And so in order to optimize this, so each block contains the time series chunks, which is the actual time series bits, and then it contains an index. And the index is how Prometheus and Thanos query all the labels. So in order to figure out what series are necessary, there's a label index. And so if a label doesn't change over the day, the Thanos Compact can combine those indexes together to create a covering index that covers a longer time range. And this allows Thanos to be much more efficient in terms of how much index data it has to look over in order to run a query. And so the Thanos Compact does the same job that Prometheus would normally do during the compaction, during a normal day-to-day Prometheus compaction. The other thing that the Thanos Compact does is it also generates downsample data. So Prometheus itself does not have any mechanisms for creating very long time range downsample blocks. Thanos does. And so basically if you've got a scrape interval of 15 seconds, that's going to create a huge number of samples to look at over the course of a month or a year or multiple years. So the compactor creates downsampled data for 15 seconds into 5 minutes. And then the same thing, it'll take those same 15 seconds and it'll generate 1 hour downsample blocks. And of course, downsampling is complicated. You need to look at the min and the max and the delta. And so there's a bunch of, and the average, so that Prometheus can actually, if you want to do, say, an average over time of a downsample blocks, the downsample blocks contain the average so that you can actually just run that average over that period of time. There are some Prometheus functions that don't really work well over downsample data. For example, quantile over time is not going to work very well. I think requires raw data in order to operate. But you can do max over time, min over time, average over time, those kind of functions. Because of course you can't, if you were to generate an infinite, you'd have to generate an infinite number of quantiles over time values in order to and store those in the time series database. So it's just not feasible. But yeah, so that covers the Thanos Compact. Thanos Frontend is a new component that we're introducing. It's basically a query optimizer and caching proxy in front of Thanos query. It's going to replace a current component that we use called Trickster, which is a general purpose caching layer in front of Thanos. The front end has some smarter things, like it will break up a query into multiple pieces based on day. So if you evaluate over a year, Prometheus tries to evaluate that all in one big query. And the Thanos front end says, oh, well, no, this is a year's worth of data. Let's break that up into day by day blocks and evaluate those individually. So you can really speed up and parallelize access to long time ranges. And the Thanos front end is going to be the new primary access that you will get to from Grafana and manual queries. That's another component of how we do this. Is there is a Thanos query. This is a standard GCP IAP. It allows you to run manual queries against all the Thanos data. And so you can do things like count by env up and see how many targets we have in each environment. Your usual Prometheus query.
And all of the Thanos components are running in the ops. Well, not all of the Thanos components, but the ones in that box are running in the ops cluster, except for the boxes here, like internal and public Grafana. Those are still running on virtual machines, right? You haven't moved those into Kubernetes.
So let's talk a little bit about the nuts and bolts of the deployment here. So all of these components are currently running in both Chef and Kubernetes, and our goal is to slowly migrate all of the monitoring components out of Chef land and into Kubernetes. It's part of the reason that we're doing this readiness review is that we're moving more of we're moving the bulk of the stuff that's in this Thanos query front end kind of cluster of services. We're moving that into Kubernetes right now. This is actually running in parallel. There's actually, so this is the Thanos query ops GitLab net that is running in that is running under Chef VMs, and Thanos.gitlab.net. Oops.
Yeah, I see, and that's running in Kubernetes.
This is the new one that is. This is the new one that's running. This is actually the Thanos front end, and this is directly to the Thanos query. So the Chef one doesn't have the front end. The Kubernetes one does have the new caching front end. And so if I query this again, it's a little bit faster.
Yeah.
But it takes 600 milliseconds for that. This one only takes 400 milliseconds.
And is there any Grafana running in the Kubernetes cluster or not yet?
Not yet. Okay. So slowly over time, the plan is to move all of it. Right now, Prometheus servers and sidecars run in Kubernetes, compact, store, query, front end, rule. Those are all running in Chef right now. But we're just about ready to cut over stores, and query front end. We're just about ready to cut. We'll probably do that next week. Is we'll be cutting those over to the Kubernetes, and we can tear down the Chef VMs for at least the querying components, and then we can migrate the compact and the rule servers over to Kubernetes after that. And then long term, there's a plan to move the Prometheus servers that are monitoring. Actually, also Alert Manager is also running under Kubernetes already. So this is this we already converted. We converted that to Kubernetes last summer. So that's been working really well.
You mentioned before that there are direct connections from the Prometheus servers in the clusters to Alert Manager. Can you expand on that a bit? Like what?
Sure.
Yeah, why is that necessary? And like I would expect, I guess I would expect that wouldn't be necessary because everything kind of goes through Thanos. But I guess that's not the case.
Querying goes through Thanos, but Prometheus still runs and evaluates a lot of data. And so even though we're doing most of our dashboards through Grafana, all the Grafana dashboards go through pretty much all go through Thanos now. There are still a few dashboards that do directly talk to Prometheus servers, but we're slowly deprecating those and updating them so that they go only through Thanos. For a long time, there were performance problems and reliability problems with all the Thanos components as we got used to operating them. That's pretty much all solved today. So there's no need to bypass Thanos anymore. It's pretty reliable now. And we've managed to figure out all the corner cases that don't work. And so, but on the individual, so if we go to a Prometheus-GKE, so this is the Prometheus server running in the, actually, if we look at the runtime, we should be able to see the, we can see the external labels. This is running inside the gprod GitLab GKE regional cluster. And so you can see that it has external labels. Then it has a Prometheus replica label, and that's the label that Thanos uses to deduplicate the HA pairs. And so this IAP just load balances over the two Prometheus servers. So if we reload this a bunch, you can see it flip-flops between Prometheus 1 and Prometheus 0, like that. And so that's one thing you have to be careful about when querying Prometheus directly. You may be getting a semi-randomized data set depending on which Prometheus server you're hitting, which is why we have Thanos in front of it. We used to have this problem all the time before we introduced Thanos. Is you would just get random data depending on which Prometheus server you were hitting in the HA pairs. So if we go to alerts, you can see that we still have quite a lot of alerts that evaluate from the Prometheus side. So things like kube version mismatch. And so because these evaluating from the Prometheus side is extremely efficient because it's all the latest scraped monitored data, and it's all evaluated locally in memory on each Prometheus server. And a lot of it is very simple things like, oh, if there's an mtail instance, are there any errors? Alert on that. And so we continue to push all the rules out to all the individual Prometheus servers. And so in the status, you can see that we have three alert managers. These alert managers are discovered if we look in the configuration using an internal DNS name that is populated by Kubernetes external DNS. And so when Kubernetes updates deploys the pods, it updates DNS, and we access that internally, and then we refresh that every 10 seconds. And so relatively straightforward DNS discovery. And then because of the way Prometheus works, when you go to alerts.gitlab.net, and we look at the cluster status, you can see that we have a gossip cluster of 3 nodes. Those IPs, yeah, they match to what we saw in Prometheus. In order, when you go to the alerts, this is same round robin. It's the same round robin problem as you do with the Prometheus IAP. This is also an IAP. The alert manager cluster populates the silences and the current state of alerts across all 3 nodes or all 3 pods. But it doesn't populate the alert messages. So in order for these alert messages to be shared among all 3 alert managers, Prometheus has to send to all 3 simultaneously. Mm-hmm. And so Prometheus is constantly sending to each of the alert managers individually. This way, if there's any kind of net split or split brain or problem, you will be guaranteed that at least one alert manager sees the alert message that goes to, so each one alert manager will get the message. It'll know whether if the gossip cluster breaks, it can still send. So it's an availability design, cap theorem design, such that it's at least once guaranteed delivery of an alert. So you can get duplicated alerts. It's a best effort deduplication of alerts, and that's important for network availability robustness. Of course, GCP's network tends to be much more reliable, but I've heard from people that other cloud providers tend to like split brain all the time, or at least have more problems with split brain in their network.
Do we run at least one alert manager pod in each availability zone, or is that not something we've configured yet?
I don't think we have that strict a configuration in our alert manager. I don't, because it runs in the ops. I don't think we have zonal cluster.
We don't. Yeah, so we would have, we'd have to figure out a way to do that. I don't know how that works.
Yep.
So what's going over the wire then is like Prometheus is just sending constant notifications to the alert manager, saying
Correct.
like this is the current state of alerts.
Correct.
Just sending that over and over again as like a heartbeat.
Every single rule evaluation that is an alert firing is sent. So if you have an alert that evaluates every 15 seconds or every 30 seconds or every 1 minute, it's just constant ping, 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 ping. And the alert manager is responsible for taking that stream of pings and turning them into one human message.
So one part I'm a little bit fuzzy on is we have these recording rules, and some of them I think are done at Thanos, right? They're not done at the Prometheus servers. So how would I be able to alert on those recording rules? Like given a recording rule, I want to alert on it if the Prometheus server doesn't even know about it.
So Thanos rule also sends alerts to the alert manager. So Thanos rule operates just like a Prometheus server, except that it doesn't scrape any data. It's only running the rule evaluation cycles for both recording and alerting. And so that's how that's how, and we'll get into that in a bit once we start talking about the runbooks and how we manage all of these rules and alerts. So let's finish covering alert manager and network overview. One thing not covered in this architecture diagram is our failsafe. Basically, there is a series on each Prometheus server under alerts. There is a snitch heartbeat, which is basically a always firing alert. And so this alert will never stop firing. And what we do is this snitch heartbeat goes from every individual Prometheus server out to the alert manager, and the alert manager sees these as always firing. And then using routing rules in the alert manager, this is the heartbeat for this cluster. It goes using routing rules in the alert manager. Where's this? Actually, I don't think I'm going to show that status because I think there might be secrets in there. We go to, so let me stop sharing for just a second and verify that there's no secrets visible in this page. So we use an external service called Deadman Snitch, which, here we go. And so each of the Prometheus servers is sending out alert messages through the alert manager out to Deadman Snitch. And so that way, if Prometheus fails or the alert manager fails, or our GCP network fails, Deadman Snitch will send a message. We'll see that a Prometheus service has a Prometheus environment has stopped alerting and notify us through PagerDuty, and so that we have kind of a fail-safe trigger to let us know that our Prometheus stack has failed. And so now that's how we kind of have this like who watches the watcher setup. There's also several other alerting rules that do similar things. So like Prometheus is monitoring Prometheus let me go back to screen sharing again. So in Prometheus Ops, so in the Ops cluster, we have a Prometheus Metamon job that from Ops, we monitor all the other Prometheus servers, or at least all the other Chef ones. We need to reproduce this similar Metamon job in Kubernetes and cross-monitor Kubernetes between Ops Kubernetes and other GKE clusters. So we need to set up external DNS and add that cross network discovery. And this allows us to detect whether each of the once we get actually, no, we don't have this yet. This would allow us to monitor and detect that a zonal cluster's Prometheus is not functioning properly, even if both of the zonal clusters Prometheuses are down, or just unhealthy, because there's a lot of unhealthy. There are ways Prometheus can become unhealthy that aren't completely down. You know, rule evaluation failures and other problems like that. Any other questions so far? All right, so we've covered Prometheus, Thanos. We haven't really talked much about Grafana, but we can talk a bit about that once we get into. Oh, let's talk about Alert Manager a little more. So on the Alert Manager, we have a variety of notification methods. The primary one is of course Slack. The next one that's important is PagerDuty. So depending on the labels attached to each alert, we route alerts to different notification methods and different teams within each notification method. So we can send low priority alerts directly to specific Slack channels depending on the team. We can send high priority alerts to people, to the on-call engineer with PagerDuty. We also have a new category of alerts that are going directly into GitLab issues. So things like SSL certificate expiries. It's too noisy to send it to Slack. It's also not very actionable in Slack. You see, somebody has to actually go look for it. But it's too noisy for PagerDuty. Like, why do we need to page somebody that SSL cert is going to be expiring in 2 weeks? That's kind of asynchronous work. So we now send those directly through a webhook into gitlab.com, and that goes into the production infrastructure project, and the GitLab creates issues so that we can and it creates incident issues that we can go and fix in a much more async way. That's still a bit of a work in progress. We're collaborating with the monitor feature and the ops feature teams to improve that and make that better for production. But it's really handy because now things like, oh, you know, we have an SSL cert expiring. oh, it looks like it's let's encrypt is the let's encrypt cron job is broken. Fix the cron job, done. But it's nice and async. We also have a thing called we also have webhooks going to Woodhouse, which is an enhancement bot, which I replaced the there was a function that was doing basically annotations on the alerts. I don't remember what it was called, but yeah, so Woodhouse is a bot that we use to basically take what we send to Slack and add some annotations to it and prettyify the output, because there's limitations to what we could do in the alert manager templating system. And that mostly covers all of our notification methods. We don't use the email notifications. We don't use any of the other notification methods. But how is all this configured? So there's still quite a lot of this in Chef. So there's in the Chef cookbooks, we take a lot of Chef attributes and Chef searches, and we turn those into Prometheus discovery configurations. The goal is to eventually deprecate all of that and move all of the VM managed services and get those into console. And then we'll be switching from Chef based file population. So if you look in the GitLab Prometheus cookbook, let me share screen again. So in the GitLab Prometheus cookbook, we have a bunch of library templating functions that generate Prometheus files, service discovery files, with all of the information manually. It's pretty awful to look at least my opinion. And it's also slow. So when you spin up a new VM, it takes until Chef is done on the VM to populate the data into the Chef server. And then it can take up to another 20, 30 minutes for Prometheus to actually pick that up through a Chef search, because we only update the list of targets in Prometheus with a Chef run. And so that cycle lag is really, really too slow. And so what we want to do is we want to move from Chef discovery so that we want when the service is added by Chef or Ansible or whatever onto the VM, it populates a console configuration, and then that is populated to Prometheus within seconds. And so the turnaround time for adding and removing a VM from creation to Prometheus is much, much shorter, almost as fast as we can do it with Kubernetes pods. Speaking of Kubernetes pods, in Kubernetes, we use the Prometheus operator. We're currently configuring the Prometheus operator with a Helm chart, but we're considering moving from the Helm chart to configure the operator to directly using the Prometheus JSONet library using Tonka. And the reason we're talking about that is because the Helm chart to operator controls make it very, very difficult to shard. And we're starting to get to the point where the individual Prometheus servers within each Kubernetes cluster are overloaded with too many pods and too many targets and too much data. And so in order to scale things, we want to split out and say one Prometheus server that monitors the Kubernetes cluster itself, and then another Prometheus server that monitors the GitLab app, and or maybe one dedicated Prometheus server just for Sidekick. And to do that sharding, the Helm chart is not flexible enough, but Tonka is. And so that way we can more horizontally scale our Prometheus in Kubernetes. Almost done. How do we configure all of these alerts and dashboards and recording rules and Prometheus? Well, that goes back to a sort of a Prometheus alerting metrics monorepo called runbooks. And so we'll go back to sharing a browser screen. And so the runbooks is a whole talk on its own. And so it kind of starts with this thing called the metrics catalog. And so the metrics catalog defines what metrics are associated with what services. So if I want to look at, say, Gitaly, in the Gitaly, we can see that we have a metrics catalog and we have our monitoring thresholds. We have the service level indicators, and basically all the core definitions of what labels are associated with what metrics. So error rate is a rate metric based on this counter and with these label filters. And so that allows us to automatically generate. So this set of JSONet using the metrics catalog generates in the rules directory, it generates an auto-generated Prometheus YAML containing all those rules. The metrics catalog can also generate the dashboards. So in order to, if say a new service is turned up, you can create a new service catalog entry. It generates the recording rules, it generates the alerts, it generates the dashboards, and you're good to go. It significantly simplifies the adding and removing or modifying of services. And I think that pretty much covers everything I wanted to talk about. Mikhail, do you have any questions?
First of all, thanks a lot for this. This has been incredibly helpful, and I'm sure this will be really helpful for others as well. Questions? No, not at this point. I need to digest all of that, and I'm sure that more questions will come up.
Sure. Cool. I think I'll stop the recording here.
So one thing that just came to my mind. So if you could just say a few words, like I'm sure that this is captured in Epics as well, but if you just say in a few words, what are the next steps for the monitoring infrastructure? So you already mentioned that we're in the process of moving most of the components from VMs to Kubernetes.
Yeah, so there's a bunch of the different Thanos services that need to get moved from their current VMs to Kubernetes. We want to migrate from the Chef-based service discovery to Consul so that we aren't dependent on Chef. And so as we discuss how to manage the non-Kubernetes infrastructure on VMs, direct on VM non-Kubernetes infrastructure like Gitaly. There's some discussions about switching that from Chef to Ansible. Once we do that, if we use Consul as the discovery layer for services, it significantly will simplify the connection of Prometheus to monitor those services. And once we have Consul, we actually don't need to run Prometheus in Chef anymore. We don't have to manage it on a VM. We can actually run a Kubernetes pod with a console discovery configuration pointed at a console server, whether that's running in pods or VMs, doesn't matter actually. We could actually run console in Kubernetes to manage discovery of VMs. Doesn't matter. Once that's done, then we can move the Prometheus servers off of their Chef VMs and into Kubernetes. And that's the long-term goal, is to get all monitoring infrastructure off of manually managed VMs. Because there's just too many problems with the way Chef orchestrates updates and upgrades. When you want to apply a new version of Prometheus, there's no coordination, and you can't specify, oh, I want to only do one Prometheus upgrade at a time and wait 5 minutes between upgrades. You can do that with a Kubernetes resource. You can't do that with Chef. If you apply an update, you get a random Chef run, and it could take out both of your Prometheus servers simultaneously. And there would be so much, there's more work involved in fixing that race condition than just moving the whole service off of Chef. And so that's the real long-term plan, is to just completely eliminate manually managed VMs, or even Terraform managed VMs, and replace that with Kubernetes services.
So that covers service discovery from Kubernetes into the VM world. Mm-hmm. Is there any reason why we would need service discovery the other way around, or do we just
no? Because the other way around is already covered by Prometheus running in Kubernetes, using the Prometheus operator, and running against Kubernetes API. So in Kubernetes, Prometheus knows how to read directly from the Kubernetes pod API and service API, and just read all that data directly. And it's even faster than console because it uses callbacks. And so the millisecond a pod is scheduled or descheduled, Prometheus gets a notification that there's an update. And so it's much smooth, much smoother in terms of updates.
Cool, thanks.